All right, so we started off this lecture of theory and what the UV-Vis instrument is doing, and we looked at really three important parts. One of those parts was a light bulb. So we said there's a light bulb here, and that light bulb shines onto a sample that we have into a sample compartment, and then something happens in that sample, and not all of the light escapes through, and then we have the instrument that has some eyeballs that we call the detector that sees how much of that light comes through. Okay, so now we need to really kind of slow down and take a look at what's really going on. We know that these samples have favorites as far as wavelength goes, and I want to dial in on the favorite first. When I dial in on the favorite, what is happening inside of the sample? What's going on as far as its interaction with the light itself? And this light could be a UV or it could be the visible portion, right? We just simply don't know until we find out what the lambda max is. Okay, well, in the early beginnings, 1930s, 1940s, 1950s, really, when all of these measurements were happening, they were reporting numbers. So the instrument does the measuring. The question is, what does it measure? In the beginning, the first thing that it measured was something called transmittance. And I'm spelling that wrong. I left out a letter. And we abbreviate that with the T. Okay. What does transmittance mean? Well, transmittance, the definition, means how much light goes through the sample. How much of it is getting transmitted to the detector. So this is my detector, this is my sample, and this is my light source. Okay, so what happens is that in the beginning, what I do is that I make sure that my instrument is blanked. Typically, this is DI water, deionized or distilled water. The DI water, the purpose of it is DI does not absorb ultraviolet or visible light at all. Okay? So what would happen is that I would take my water and I would put it into this sample compartment and I would turn the bulb on, and the bulb shines through the water, and all of that probably will go through, and the detector will measure how much is transmitted to it. How much of it is coming out the other end. Sometimes we'll call this P nod, and this one is P. The reason P nod is used, that zero, think of that as that zero meaning an O, and O stands for original. So this is the original amount of light coming into the sample. I put my DI water in, and the majority of that will go through. And the detector says, okay, this is DI, I am blanking myself. So this is my tear option. Blank is very similar to tearing out a balance, making it read 0. That's what we're doing here. So the light shines onto the sample. The sample, a couple of things can happen. The molecule can interact with the light, or the light can bounce off. So depending on what's in there, a part of the original light comes through. And that part that comes through is measured, and that's what we call transmittance. How much light goes through the sample. If it's DI, almost all of the light will go through. And if almost all of the light goes through, then that means almost all of it is transmitted. And that means 100% of the light is transmitted through the sample. We call it percent T. The reason we call it percentage is because it's easier for us to measure and think of it in terms of this. So if 100% of the light is going through that sample holder, then that means the sample's not doing anything at all. However, depending on what we put in there, sometimes only 90% of the light can go through, less of it. Sometimes 60% of the light can go through. Sometimes 40% of the light can go through. And sometimes 0% of the light can go through. The sample blocks everything, and the detector doesn't see squat. Okay, so almost all of the light will go through, meaning almost all of the light is transmittance, which means that this is a very high percent transmittance rate. The problem with percent transmittance is that it's no longer used. And the reason is because it is nonlinear. And if you've participated in this before, or if you've done another class with us before, nonlinear is a problem. We love calibration curves that make straight lines. 0.99999 or a perfect 1 is what we go after. However, these nonlinear curves cause us an issue because it's really hard to do data analysis with it sometimes. So because of that, percent transmittance is not really used in a laboratory environment anymore. So the very early on instruments had a percent T or a transmittance value that it was giving. And this percent transmittance value caused us problems, but we dealt with it. The newer instruments, though, those are defaulted to another setting. They are not percent transmittance machines. But we can go in and we can switch these new machines over to percent T, and that will allow me to make measurements like the old timers used to do it. However, we've gone above and beyond that now. We do not use percent T for really anything at all. And what we use now is something called absorbance. So in the next video, we will talk about this definition of absorbance, what it is, what it does, and why it's so important, and why we use that over percent transmittance nowadays. There's got to be something special to it, right? If you want an equation to calculate transmittance, they're out there. Transmittance is equal to the light that has left the cuvette that hits the detector divided by the light that was coming through the sample and into the detector in the very beginning with nothing in it. And then we can multiply that by 100 to get a percent transmittance. So that is the equation. If you're asked to calculate transmittance of something, take the original light, take the remaining light, divide the two and multiply by 100, and that is percent transmittance. Okay, so in the next video, we'll talk about absorbance and a little bit more about it and why we use it. So don't leave me yet. We're getting ready to talk about the next best thing.